Now, before we are continuing, I want to give you a quick intro into cryptographic hashing. And it's not that, that I don't believe that you don't know cryptographic hashing. If you know everything about hashing, then feel free to skip this lecture. If you think there might be something that you can still learn, then stay on. So this is just a quick intro. So what is hashing? What happens during hashing? You have some sort of hash function. And in this hash function, you usually send in something and get out something. So let's say in a hash function, it might be an SHA-1, SHA-256, KZAC hash, any other hash function that you come across. MD5 is one, you might have heard of it. You send in something and get out a digest. It's called a digest. So let's say you send in hello Rome and you get out this digest 398BDAF and so on. And then you change one character, you add an exclamation mark, hello Rome, exclamation mark, and suddenly you get a totally different digest, D2, B3, C5, D9, and so on. So what is happening here? The different parts of a cryptographic hash function are the input, that is something we send into that hash function. Then you have that cryptographic hash function that does something with the input, and it produces a so-called digest. There are 5 properties that every hash function has. So these are the 5 main properties. The one is it's deterministic. So if you send in hello Rome and then send in hello Rome again with the same input, it produces the same hash. It produces the same output no matter how much time passed, no matter on which machine or where you are, it's producing the same output. So it's deterministic. Number 2, it is very quick to compute the hash value of any given message. So it cannot take forever. It's sometimes beneficial to slow that down in case to avoid any brute force attacks, but it's still fast enough that you don't have any measurable lag. So if you interact with a system, then you don't need to wait 5 minutes or 10 hours or 3 days, that you can continue with your work. It's quick to compute the hash value, so the digest for any given message. The thing is, you shouldn't be able to go back. So once you have the digest, it should be infeasible to generate the input from the hashed value, except by trying all the possible messages. So a brute force attack, it should be the only viable way of getting back to the message, and this one should take very long or pretty much forever. And when you change a small thing, like I showed you with the hello Rome and hello Rome exclamation mark, it's just a very tiny change, then the digest, the hash value, should be completely uncorrelated and very different to each other. So you have totally different hash outputs, digests, to very small changes to the input. And the last one, there shouldn't be any collisions. So it should be infeasible to find 2 different messages with the same hash value. So one problem with MD5 is that people found a couple of collisions and found that it's in general not a really good hash algorithm. And SHA-1, I think, has the same problem now. It's better than MD5, but it's still not very good. So SHA-256 is right now the go-to hashing method, and the KZAC hash is also considered safe as far as I know, but I am by all means no cryptographic expert, so do your own due diligence, please. Now, what is important to understand is how hashing of hashes work, because this is what the blockchain is actually building upon. This is what is the power of blockchain. So let me show you what I mean. Let's say you hash ABC, and let's say you hash CDE. And for whatever reason, we are doing this with color coding here because it's easier to understand. So if you mix those 2 together, you're getting a greenish color, right? Blue and yellow is green. And that's what we learned in school, color theory. You mix them together, fine, green. Now you're going to hash 1, 2, 3, and you're mixing this, you're hashing together the green and the red. So basically our hash function for the colors is a pure mixing. Imagine it's like a pot of normal color of paint, and you mix this together. If you mixed it once, you have a hard time to separate them again. So let's say this is our hash function. So if you mix green and orange or yellow together, let's say you get this brownish color. Okay, now you change something. You change the hash from CDE to CDF, and the hash from CDF is not the yellow color anymore, it's the purple. So if you mix blue and purple together, you get a dark purple. But then suddenly the dark purple is not the same as the brownish, as the bluish. And if you mix the dark purple together with the orange, you get an even darker purple. So this is not the brown that we got. So everything down the chain changed by changing one of the input values. And this is what the blockchain is about. With blockchain hashing, it works very, very similar like the thing that I just showed you. You have a block that might be a blue color. You have transactions that might be now in yellow. If you mix them together, you get a green. Okay, now you have a green block. You have transactions again. You mix them together, you get a purple. You have a purple, you have a gray block with transactions. You mix them together, you get a lighter purple. Now you could go ahead and say like, there was a transaction here. Let's change this. Let's make this a different color. Okay, because I'm in control of everything. Okay, if you mix these together, let's make this a different color. And then obviously you have to make this a different color. So everything that came afterwards is then a different color. But because we are in control here, it's on our database maybe, we can do that. It's maybe inconvenient because we have to rewrite a lot of data down the road, but we can do that. Now the trick with blockchains is to take these hashes and to have a copy of these hashes on every blockchain node that is running. So if you want to change one thing over here, you somehow need to convince all of the other blockchain nodes that they should do the same thing, but you cannot because that is not what the Ethereum protocol allows. That would mean to actually do something like a hard fork where you have to have the actual people that run the miners agree to do this change. And this is where the power of decentralization really comes in. And this is why the blockchains are considered so secure. Okay, our key takeaways. Hashing is the mathematical foundation of blockchains. There's no other way to say this. This is the base of why the blocks are chained together, because in every block you get a hash of the previous block. Changing information in a previous block changes all blocks after the block where you change the information. So you cannot just go in and change a block's information without changing all of the other blocks too, because then the hash of that block would be different. You remember, small change in an input, large change in the digest, so that the hash would be totally different. And then that hash is stored in the next block. So if you hash that hash, it's a different hash that you hash, and so on and so forth. So it wouldn't be feasible to do that. And blocks are stored decentralized by being stored on every participating blockchain node in the network, and they are re-evaluating the hashes because it's very quick to do. You can hash a previous block and compare it to the hashed output, but you cannot go back. But it's a very good way to have a checksum. That's it. That's what I wanted to talk about hashing. I hope maybe a few things are more clear. And now let's go on to the next lecture where we are talking about the transaction in more detail.